Welcome to the do-over version of the computer architecture. Boy, there's a lot of movement. Okay, we are settled. So my goal was yesterday to give you a, let's say, a little bit harsh introduction into the MIPS architecture. My goal was to get 50% understanding, and 50%, was that okay from yesterday? 50-ish? Not even that? Okay. Maybe today we will get to 50. So what we will do today is we are actually going to repeat it, but I will now rely on the slides, the second part of the slides. I'll just make a very quick recap of what I was talking yesterday so that I can tie it to today's lecture. So what we were discussing, and I'll just very briefly do something on the blackboard just as a, me playing with chalk kind of thing, so that I, don't lose the capability, but I'll mainly stick on the slides. What we wanted to do is, we said, hey, we now know what the architecture is, we now know what kind of instructions make up the instruction set of MIPS. We said that there are R-type instructions, I-type, J-type. We never talk about this J-type, but whatever. There are these type of instructions, and we said that everything is posted in a memory somewhere, and there is our program will get memory as a series of ones and zeros. Not for long. Okay. So much. I can speak louder without the microphone, okay? I'm not going to prove it to you. I need my voice. Wasn't very important what I said. We were talking about implementing a processor, MIPS processor. So this is our goal for today. We decided on the architecture. Somebody decided what the instructions were, what they can do, what their capabilities are. We said that there were made some compromises so that they can be implemented easily in hardware and we don't have too many instructions. Last week, I showed you that even though keep it there. Even though these instructions are not so spectacular, by combining them in the right way, we can actually realize a lot of things. Now I need to again do this thing, my God. Don't record this, I'm trying to press OK here. Okay, good. Whew. And we also discussed that the programs that we write could be converted to these instructions. Those instructions have a one-to-one correspondence in ones and zeros, and those ones and zeros could magically be placed somewhere in the memory, and every location in the memory, in this case, holds a 32-bit word, and some of these are the program, our instructions, and the program counter would be showing where to pick the instruction, and we would execute it. What do we do? What is our job? This is on the slide there. So we go and fetch, we find an instruction. It's the first thing that we should do. And then we look at those ones and zeros. What's inside here? What's the content? What are those 1, 1, 0, 1, 1, 0, 0, 0, whatever it is, tells us what to do. So decode what the program wants us to do. Decode it, understand what it wants. What it wants. And then the next step, most of the instructions we talked about require operands. We want to take two operands, merge them, create something else. So we need to find where our operands are. So find the operands. They could be immediates, meaning that they could be encoded in the instruction. They could be registers, or they could be read from the memory. Then the next step is to do what the instruction tells us to do. So execute whatever he tells us to do. And in most cases, we argued that the brain of the processor
is something that does all these computations, and there is like this arithmetic logic unit that can add, that can subtract, and that can do a few other fancy stuff. So most of the time, we'll be doing something in the ALU. Let's cheat. After this operation is done, we will have a result. So this result will go somewhere. We will write back the result if we create one. Write the result, and the result could go to the memory or to the register. And once we have done this, we will start over. Meaning that we will jump here and fetch another instruction, tell what it is, continue doing this. So this is what the microarchitecture should realize. And at the beginning of the lecture, we said we are going to realize this entire thing in one cycle. We will make a digital circuit where we have a state. We will start with, so this is me redrawing it very briefly and not in great detail, so I'm allowed to make mistakes. So somewhere we will have a register that holds the program counter. Now, this program counter is going to go into a memory which holds the, so there is an address, it's a 32-bit address that enters here, and corresponding to this address, there will be a data out that comes out, which contains the instruction that I'll be dealing with. So this is the data memory. And so far, this first part that I did does this part, right? I fetch an instruction. How do I fetch it? Well, the program counter points to a place in the data memory, and corresponding to that address, there is the instruction, it comes out. We realize that the instruction has different bits telling him what to do. There are special things that says, hey, this is an R-type instruction. Well, the R-type means that data is found in a register file, or register file, register array, something like that. It has 3 addresses. So 2 of them for reading. So this is the address 1, this is the address 2. So I can find 2 operands in the register file. I have 32 to choose from. This means that I need 5 bits to tell them apart. And for every address, I have a corresponding, not this one, sorry. I have a corresponding output of 32 bits. So this is the read 1, this is the read 2, sorry. Now, part of this instruction contains which register I am choosing. I can pack them because, you know, there's 5 bits here, 5 bits here. A few of the other bits tell us other things. So, you know, I can manage this. And coming out of here, I go to my ALU, which says, hey, I will do some sort of operation. And say, hey, I have an input A, I have an input B, I have a result. And you say, okay, this one provides the first input, this guy provides the second input, and I have an output here. And what do I do with the output? Well, right now I have, if it's an R-type, register-type operation, if this instruction that came out is of R-type, I have chosen the first register, I've chosen the second register, I got those 2. I went into this ALU, some part of this instruction, like secretly, told me what type of operation I should be doing, or function. And I have my result, and now I know that this result will go back either to memory or register. If it's an R-type, it should go back to the register. Okay. Where do I find where it goes back? There is a third address here. And the write data. So the data comes back. And the address comes again directly from the instruction. So this completes the cycle. I fetched an instruction. I decoded and understood what it was. In this case, it was an R-type instruction. And then I found the operands for my instruction. Those guys were found, in this case, the register, both of them. And then, so I did this part. And now I executed whatever it was wanted from me. Whatever was wanted was in this function here. It said add these two things or subtract them, whatever. I produced the result. So in 32 bits, it's 32 bits so that we are clear. And then the result came back here and we wrote it back to the register file. We also had to make sure that we are writing to the register file. There is some control signal that says rec write. Okay, okay. We did it. Now, we ran our instruction and we wrote the result to the back. Now we need to start over. So this program counter has to point to a new address. And how we did this is we also manipulated this program counter. We said, hey, you guy needs to be added. And I need to add the constant 4 because we have word addresses. And we take that output and make it the next PC. So this is the PC, this is the PC next. And this is PC plus 4. And that's it. So that would take care of this thing. So if this processor is doing only R-type instructions, we are done. We realize this is not the case. So somewhere there was also a data memory. And we had some issues that we wanted to write. We had some, we could read from it, data output. We could write to it, we had the write enable, we had these things. So we had instructions that would write from the register file to the memory, or read from the memory and write back to the register file. And we were discussing how we would manipulate it. And then we realized that we need to put some multiplexers because data was not always going the same way. Sometimes this data was going back here, sometimes it was jumping over, so we made these choices. And all those choices created this program, this control part of the processor. Now I'll just get rid of this part. So this is more or less what we were discussing, or I hope what you remember from yesterday. Okay. It's disappeared almost. Good so far? And now let's go and stay on the slides like real humans do. What is that? Playing with chalk. We are grown-up people, right? No, we are not. Okay. Shut up and... Oh, there's too many things on the chat. Ah, it's good. Okay. Good. Room. Okay, we stay on slides now. What are the basic components? So we discussed, we had the memory, we had registers to access, we had a data memory to read and write to, we had an ALU to perform things. We will see very shortly, once again, we saw briefly yesterday that these are, if you want to describe them in Verilog, individually, all of these things are actually very simple. When we combine them towards the end of today, you will see that their connections are also very simple. Those are modules, have inputs and outputs. They are connected one way or another. And most of the time, there's a multiplexer allowing you to have a choice between, let's say, taking this input or another input, or taking it from here or from there. And those control signals all come based on the decision when you make the instruction decoding. You take a look at the instruction. The bits of the instruction tell you what type of operation we should be doing. There are some additional auxiliary pieces. We need to have the program counter to tell us where to pick things. We need a way to manipulate the program counter, which the very basic one is this one, where there's no branches, no jumps, nothing. I mean, it just continuously increases, as well as some logic, which is the magic that we are not touching too much. Always it goes down, comes up magically, that part. That decodes the instructions and decides on the value of all these multiplexers and control signals that go there. So the program part we had, and we briefly discussed about this. So this is just to give an example of what happens with this part that I have just drawn here. In this case, this is exactly this part. present state of PC plus 4 is the next state of the program counter. And when the clock comes, well, if there's a reset, this is the default value of my program counter. So when I press reset, I know where to look for the program. It's not some random location. And otherwise, every time there's a new clock, we start from this location, go 4 more, 4 more, 4 more, and hopefully at some point the program will have done what it is supposed to do. Now you look at this box, and this is a description for it. I mean, my only hope is from this slide that you realize there's no need to be scared of it. Once I define what it does, and the definition is, let's say, tangible, is simple enough, the corresponding description of it, writing it in Verilog or in any other hardware description language, shouldn't scare you. Is it scary? Okay. Well, nightmares can be made from Verilog, right? Anyway, what we wanted to do is, and what we will do and did and do again, is to talk about a subset of MIPS instructions as a placeholder for most of the others. So we will cover the simple and, or, add, subtract, as well as the set less than, the memory instructions, load word, store word, branch equal to, and then discuss a little bit how we can also add a little bit more complex things. Those 6, 7, 8 instructions actually do most of the work. Sure, there is another 40, 50 of them that make up the MIPS instruction set. They are back in the appendix of the book. But once you figure out how these are made, the others is just more of the same and a little bit of details here and there. Questions? Great. I love when the entire audience is sleeping, so nobody asks questions. Okay. We talked about R-type, and it was called register type because 3 registers are involved. 2 of them come in, and the result ends up in a third one. The instructions to tell one instruction apart from another one, people have agreed on a notation, on an encoding for those 32 bits. And looking at the first 6 bits actually tells you what type of instruction we have. The discussion was made that, hey, R-type operations have it all zeros. And inside R-type operations, there could be many different ones. The last 6 bits tells you what type of operation we do. As an example, 32, 10000 was supposed to be add. Just to show you how difficult it would be if we just had machine language, 100010 would be subtract. It's much easier to have the assembly level instructions where we can understand it a bit better rather than talking about the machine code, which is all zeros and ones. This, however, is ultimately what ends up in the memory. Then we talked about the register file, so this guy here. And since we realized that R-type instructions need at once 2 32-bit values, calculate something and write it back, we say we want a special memory. This memory is small, therefore I can afford to make it special. A big memory, like the data memory or instruction memory, would be too expensive because those things hold thousands of words, whereas this guy is relatively small, 32-bit values. If you want, those are 1,000 flip-flops. It may sound a lot, but compared to what we can do on a chip, on an integrated circuit, this is a relatively compact thing, so we can afford to make it fancier. In this case, I can supply 2 addresses that deliver me 2 outputs at the same time, not one after another. So this is how the register file looks like in a description, and you can easily see that, hey, I have an array, 32 of them, each one 32 bits, and you realize that the moment I supply this address, I'm going to get an output. The moment I supply this address, I'm going to get an output. 2 in parallel, they could be the same. Nobody says that they have to be different. The only thing is for writing, this is when I have a clocked event. And if write enable is here, well, there is the address. If there is write enable, whatever is at the input here will get written to that location. And this one can override some of these guys because the way it goes is I read I generate something else, and the next value is waiting here. The writing will happen when the clock comes. So I can take S0, modify with S1, and write back to S0. There's no problem. I'm not overwriting the same thing. It will be overwritten on the next clock cycle. This is how we were doing all the digital circuits. Now a little bit trick. This is like the simple form. Then we go and look at the MIPS architecture description, and they say, you do have 32 registers, but not all of them are the same. Some registers are more equal than the others. So those ones, we said, if the address, the register 0 is special, it always contains the value 0. How could we do this? Well, one way would be to discipline everyone on Earth and saying, if you're writing MIPS code, compiler guys and assembler guys and hackers and everybody who wants to break into systems, make sure that the value 0 stays there. But you might be a suspicious type of person. You may not trust software people. Who thinks software people are trustworthy? There goes your mistake. Okay, so you can put something there and say, hey, if the address is not equal to 0, then take the address, otherwise just return 0. That in hardware already prevents you from, let's say, writing anything into the register 0. It's just a small trick to show you what we can do. Now, the next one was the heart of the operation, and we saw this already in the previous lectures. I'm not talking about yesterday. We saw it a couple of weeks ago, and this was a combinational circuit. We had 3 inputs that selected a bunch of different operations, and based on the F function, I could AND, OR, plus. This one was not particularly useful. I could do these operations, A minus B. And then we defined this funny operation, set less than, where we actually subtracted A from B and then looked whether or not the result was negative. And if it was negative, we just sign extended it, or we just took this 0 extended and had either a 0 or 1. We discussed this operation last week when we were doing loops and comparisons. For less than comparisons, we were using this interesting operation. We discussed this more in detail just after the combinational, or at the last part of the combinational circuits lecture. If you click on the YouTube video for that, you can see that. So that was most of the components for MIPS. We don't have data memory. We can implement all R-type instructions, but we don't have much else. So this is where we were yesterday. And we can also briefly take a look at how this memory looks like. Nothing very interesting. Again, we have an array. This time I have 65,536 words of 32 bits each. This means that I need only 16-bit addresses, whatever. And the moment I supply an address, I have an output. If I want to write, I have to put the write enable, and whatever address I'm pointing to will be overwritten by whatever comes in here. That's my data memory. And now we wanted to read and write into the data memory. And we realized that we have these funny type of instructions. We didn't have the data address, the location that we write directly. We had this interesting instruction. So if we want to read from the memory, we said, I want this register, I'm just using one random register, S0, to be read into from the memory. Somewhere, I have another register that points, that's a 32-bit value. I'll just pick T1. And this register, we said, contains a base address. But not only that, but I also have an immediate, a constant value, which I can use to manipulate this address. We saw the uses of this last week when we were, for example, talking about stack. The stack pointer was showing us where the stack is, and then the first word was 0, the second word was 4 after, the other one was 8 after. So it made programming or writing or describing these data structures easier. So I have a constant here, whatever, I'll just write a random value, 24. And where do I find the data? Well, the data is, first of all, comes out of this register, but not only the register, plus this constant. Now I realize that, I need to generate this 32-bit address here. I can read out the register, but it's not only the register. It's the register plus some constant. So you say, where's the constant? Well, the constant is encoded in the instruction, the first 16 bits of it. I can take this constant and I can expand it and add to the register. I can reuse this ALU and tell him, take the register, take the constant, add them together, and then we have a result. So this is what we were doing. And so we have a different type of instruction. I need two registers. One of them showing me the base address where the memory will be. One of them, the register that will be read into. Then I have the constant here. So this constant will be, I have 16 bits to encode it. I'll probably manage to write 24 in those 16 bits. And we make some changes, not in the ALU directly, but around the ALU. So we need to manipulate some of its inputs. It's no longer reading, the second input no longer comes from the register file, but I put a multiplexer and saying, yeah, sometimes you take it from there, sometimes you take this instruction, blow it up, the immediate, blow it up, and then send it to the to this thing. Let me hide this ugliness here, and we will see it in the slides in a few seconds. Writing to the memory is similar. But in this case, when you have a store word, we still calculate the address the same way, but this time, this address is not the one that shows where the data will be written. This is the source, and this value will be copied into the data memory. So we are going to bring this value, the register here, and we are still going to calculate the address from here. So there are, again, a few differences in happening. So what we realize is that the data path has several options. The ALU may have its inputs either from this register file, or it can be an immediate. The address of register file can either come from let's say bits 21 to 16, or it can come from 15 to 11. We saw that there's a difference where we are picking this thing between the R-type and I-type instructions. We can enable a write here, or sometimes we are not really writing something back, so there's no need also to enable it. We can enable the memory, tell that whatever is here should be written. We are not always writing it. Sometimes we want to, sometimes we don't want to. And all of these options end up being our control signals. So what we do is we develop our control table. And for all the multiplexers we have here, don't worry, this is coming once again, okay? There will be yet another one, the same one. And we have a number of things we discussed yesterday. There was this thing, and am I having a write enable for the register file, this guy here? Am I writing to the address shown by RD or RT? So this was this multiplexer that chose the A3 here. Is the ALU input coming from this one, or is it an immediate? Am I writing to the memory? Am I writing back? Is this result coming from the ALU, or is it coming from the memory? And what type of operation does the ALU do? Those were the decisions so far, or at the beginning, that we saw. And it's actually not so difficult. Once you start filling them in, you realize that all R-type instructions are recognizable by the fact that the first 6 bits are 0. So our logic, our control logic, which sits down, should definitely take a look at those first 6 bits, because those 6 bits tell us a lot. Once those 6 bits are 0, I will always be writing to the register file. There's no alternative, let's say. Then the second one is the destination will always be a register. That's why it's an R-type operation. There's 3 registers are involved. We read from 2, we write back to 1. The ALU will always come from the register file. I'm not writing to memory. The results don't come to memory, and whatever the ALU is doing is encoded in part of the instruction that are in the lower 6 bits. I know it's boring. Good so far? Okay. Now, why do I care about this table? Because if I change the instruction, things will change. How do I realize that I changed the instruction? Because the opcode, the first 6 bits will be different. In this case, load word is 10011. I will still write to the register because guess what? When I load it, in the end, I'm writing back to the register file. But the rec test, I'm not choosing the same destination address as here because in the R type, I was using the lower bits. These guys are here and immediate. Yes?
So it says we write to RT or RT, but our register file only has one write.
No, I mean, maybe this wasn't written very nicely. Write to register, write to the address. It's not nicely written there. So there are in the R type, where shall I do it? Let me do it here. In the R type, so this is the R type. Good question though. So let's quickly have this. It was missing 031. So the first 6 bits are the OP, and then you have 3 registers in the R type. In the I type, you have 2 registers. Okay, so this is immediate. This is register 1, this is register 2, this is register 3. I can never memorize which one is which, so I'm writing R1, R2, R3. Of course, I will demand that you know them by heart. I'm evil. They said 20% less jokes, right? Okay. They didn't say love 20% less. They said I should make less. Okay. So the difference between R type and I type is the destination register for load word and the destination for this thing are at 2 different positions. So you need the multiplexer there. So what this guy chooses is, do I find the address where I'm writing back from this location or from this location? So that's what it tries to say. And I agree with you, it's not written very nicely. Yeah, it's not there yet. It will come. I still have an hour. Okay. The store word now is again a different instruction. And you can see, for example, in a store word, I'm writing to the memory. So the memory is enabled. I am not writing to the register. Since I'm not writing to the register, I don't care what this input comes from. I'm not writing to it. Whatever makes life easier for you. I mean, you know, it's me communicating my intention to the synthesizer, which will take my code and turn into real actual circuit. And I say, it really doesn't matter if this value is 0 or 1, because that address will never be used. I'm not using the write enable during this cycle. If it helps you, if it makes a smaller circuit a nicer circuit, pick 1. If it doesn't, pick 0. I don't care. So this allows us to do some of the optimizations that we were talking about during the combinational logic parts. Now we are much, much better. Almost all components are there. Most R-type instructions are there. We can read and write to memory. This is good because R-type instructions only worked on these register file, which is not much, only 32 of them. But now we unlocked the keys to the kingdom. I have this entire memory, 4 billion words, 1 billion words. I can read and write to any one of them. I cannot do it directly. I first have to take it from data memory to register file, operate on it, and once I'm done, I can write it back. If you remember the way we were calling functions, we were constantly copying things back and forth. So a lot of a program in modern computers is moving, shuffling data left and right. In between, we do something useful. And what we don't have are anything that allows us to manipulate this program counter. our program always picks the next instruction, next instruction, next instruction. It's in computer terms, it's a completely unrolled program. Every instruction follows each another, and at some point, I'm going to run out of instructions, and hopefully, Y2K problems, whatever the world will end, kind of thing. So we need to have some instructions because this doesn't make sense. I need to be able to make loops. I need to have flow control. And for these things, I need to have some branches. So this was also what we discussed. When you go to the appendix, there's an instruction that has this opcode, and it makes the following. It checks if the two registers are equal. If they are equal, then the program counter should be manipulated. How? Well, if I wasn't doing any manipulation, it was already pointing to 4 more. And on top of that, I will add whatever immediate, whatever constant I have stored in the branch equal to instruction. So I compare these two registers. If they are equal, I add the value, that constant, to the program counter. How do I do that? Well, we can use our ALU because it's already there, and we can subtract these from each other. We need maybe a special signal, so this was one of the things that came out today, that says, hey, is this 0? So this one goes this way, goes to the control and says, hey, I subtracted these two, I have a value, and that value is 0. If this is the case, then I can add to this immediate value and somehow add another multiplexer in front of it and say, you're not being incremented by 4, you're being incremented by 4 plus whatever that constant. Yahoo! The problem is, I already did one addition here, I have nothing left. I did one addition here, I have nothing left to do this additional addition. So bad. And I have to add another adder somewhere here. We realize that this is not going to go any different. Don't worry, we are going to come back to the drawings, okay? I mean, I'm not relying on this one only. Okay, now for this instruction, yet another opcode. I'm not writing neither to the register nor to the memory, and I am manipulating now that I want to do a subtraction. I'm reusing the ALU for a subtraction, and I have a new control signal that says, guys, I'm branching. And guess what the branching signal does? He will add a multiplexer here and say, hey, it's either PC plus 4 or the new branch target address that will, I'm not drawing the rest of it, choose this thing. Are we jumping or not? So, we are almost done. We have conditional branches. What misses are probably the absolute jumps. So I can jump relative to where he was. And I told you that we are never talking about this J instruction. It's not true. We love J instructions as well. So let's just take a look at what will be happening there without making too many modifications. So the jump type wants to actually give you the complete address where we should continue, all 32 bits of it. The problem is the J-type instruction is also fits into 32 bits. And I had this very cute idea that the first 6 bits should tell us, so the 6 bits should tell us what the opcode is. The rest I can use for an immediate. But it's only 26 bits. I can only encode 26 bits. I need an address of 32. How hard can it be to get 6 extra bits? Well, we are going to do a lot of tricks for that. The first trick is to realize that whenever we make a jump to another location, instructions will always be at the word boundaries. This is a choice that MIPS designers, the architects of MIPS, decided upon. It was given as that. So if this is the case, and you know a bit of binary, which you all do, the last 2 bits will always be 0. So if they're always 0, why bother even encoding them? So my 26 bits become 28. I am, 1/3 the way to achieving 32 bits. What will I do with these rest of the 4 bits? Well, look at it. You look at what your options are. I mean, you could randomly have some bits there, 1101. You could say, you know what, it will stay in the same vicinity. So wherever we are, whatever is our current address, let's just pick the first 4 bits of the current address and copy it. Is this perfect? No. We cannot jump everywhere, you know, so the entire memory is 1 billion words, right? 4 billion, 32 bits is 4 billion. 4 billion bytes is 1 billion words. So I cannot jump to anywhere in that 1 billion words, but I can jump anywhere, what is 16 divided, yeah, well, every 64 million words, I can jump back and forth. It's not such a bad compromise. So this is what they end up doing. So if this is the opcode, the program counter will be equal to this jump target address. And what we will do is we will take, you know, this is always our address. If we weren't jumping, our address would always be PC plus 4. So let's take the first 4 bits of whatever PC plus 4 is, add our immediate, and then add 2 zeros. Necessity brings us to some compromises. Once again, if you are the architect, and I hope some of you will pick up being a computer architect, you could come up with different ways of encoding. You could make different compromises. You could, for example, say, hey, I have a special instruction. If this one comes, read another 32-bit word in the memory, and that 32-bit word is the address you're jumping to. You could do it. The people who were devising MIPS said, no, I want to make sure that every instruction, regardless of what they do, can be encoded in one 32-bit word. And I will do that. And if I have to do some silly tricks for those direct jump addressing, I'm going to do it. Most people, 99.9% of the people will not realize. Frank will ask silly questions in the exam, and people will complain about it, but that's about the extent of it. Not even an exam makes fun. Okay. So for the jump, we have maybe some other things. We have added another one, and guess what? Of course, there will be yet another multiplexer coming somewhere in here, and well, maybe it will come here. And so that one will be then the jump target address, 01, whatever, another control signal will come here and say, are we making a direct jump, yes or no? And, well, we are almost done. There are still things we can improve. We can add more functions into the ALU. There was always, when you talk about the R-type instructions, there's always this shift amount that had to do with the left shift, right shift, arithmetic left shift kind of things. We didn't really talk about it, nor did we implement it. We could have do this. We could add a multiplier. We only had load word and store words. We can have more J-type functions. So to be able to complete our processor. So this completes our architecture. Now what we are going to do is we are going to take a break, deep breath, and then after the break, I will, believe it or not, repeat it once again. Yeah, I know. But this time, what I will do, because this, what I repeated, is actually what I was talking about yesterday. Now, in your book, for the record, there was also some feedback about it. I am trying to follow the book as much as possible. All the figures, all the examples, all the tables are directly from the book. Sometimes I don't like the examples, like the snail. I really hated that snail. I'm sorry, Harris, if you're watching, David. I'm really sorry. I really hate that snail. I will go back to the original order that is with the book and how the operation is listed in the book. They have a different order of how they show the instructions, and this time I will use the drawings and figures as they are in the book. If you're watching in July, this is the part you want to watch in 15 minutes. Thanks a lot.
So last year,
Yeah, this time also.
now you brought
Oh, I'm taking the instructions from you. That should have been instant.
yeah, okay. I wasn't sure, so I did.
Oh, come on, I'm taking the instruction out of there. That tells me what to do.
Yeah, yeah. I want to ask you the question. Now we have the ability to save memory, right? Data memory. But I mean, obviously, like a hard drive is an important part of the computer. So, what kind of instruction or like how do we save like long term? I mean, it's quite slow, obviously, right? So,
We will come to it at the very end. So there are two ways how you go to the hard disk. The first one is that you see that this memory, you can address up to 32 bits, so 4 gigabytes of memory, right? You probably, in every computer you have, you don't have the entire memory available. So part of it is will be a virtual memory. And some of those virtual memory addresses could physically be placed on a hard disk. You will not realize it. For the processor, it will be transparent. You will put an address and you will say, I want to write to this address or I want to read from this address. You will see that outside of the processor, shitloads of things will happen. We will use caches which make it look like the memory is much closer and much faster. And we will have virtual addresses which, although I say I want to go to this address, he says, he thinks he wants that address, but that address is actually somewhere completely different, and I will manage it. There will be pages, and some pages that don't fit into the physical memory on the computer will be copied onto the cloud, onto the hard disk, and other things. Now, the other part, so this is transparent to the processor. The processor has no idea that this is happening. The other part is you might have peripherals attached to your computer system. And one of the peripherals could be an Ethernet card, it could be the graphics card, it could be a hard disk controller. And the operating system here wants you to access that device, copy some data to it. This is not the same as the instruction telling you to do so. This is on the operating system level. The higher level, the application accessing a device and wanting to do the same thing that these instructions would be starting, let's say, the Google Chrome. They will write to the screen, they will send data packets over the internet and get it back. The sending data packets, writing to the screen, getting haptic feedback from your touch screen, those things will happen over devices. Those devices will interact with the operating system over device drivers. And the operating system will give function calls to the applications. And those applications will get messages and signals and everything else, little programs running in the background making this possible. Because the device driver, guess what, will be a location in the data memory. And at a certain point, when you write to that place, you know that those bytes are getting sent over the internet as a TCP/IP packet or as a UDP packet or something. So there is a couple of layers on top of that when we come to hard disk. There is one layer which is direct, where the processor doesn't realize where things are being written because we are being annoying and we put things in between. But the processor doesn't think that he's writing to the disk. He just thinks that he's writing to like this gorgeous memory. He doesn't know if it's a DRAM, he doesn't know if it's an SRAM, he doesn't know if it's something like this. He says, this is a 32-bit address, this is a data, write it. I say, okay, I'll do it. And the processor is not going to, but did you write it to an SRAM or did you write it to a hard disk? And the other guy says, don't worry about it, your data is safe. The difference that you see as a user will be sometimes when you ask for the data, it will be like, here's the address, give me the data. Data, hold on, because why it's in hard disk, things are spinning, data is being read out, it was copied, comes here, and like, I don't know, 5 million cycles later, here's your 32 bits. want to say on it. Thank you. We will discuss these. We will discuss the memory hierarchy, virtual memories.
We wouldn't know to wait, right? We would not know when to wait. Like
the processor would know when to wait. Because
we're thinking that we just write memory, right?
Yes. So I tell you lies all the time. So I simplify things and make life simple. In our simplified world, every cycle I can write to the memory and read from the memory, which is not a very bad assumption. This was the case in, let's say, 1980s. At some point, this comes in like 2 weeks when we are discussing about memories. We realize that we can no longer make memories as fast as the processors. So I can make this operation faster and faster. But when I make memory, the only thing that counts is not the speed. It's the amount of data you can hold. People want to pay for large memories. They don't want to pay for fast memories. If they have to make a choice, no, but if nobody, I can guarantee you, nobody will buy DDR6 if it is 1/10 the size. So you can go and say, you can have 1 gigabyte of DDR6 or 32 gigabytes of DDR4. Let me see to make that choice. If they are both 32 gigabytes, you will buy the DDR6, that is true. But if you have to make a choice, do you want to be 50% faster or do you want to have 4 times density below HV? I mean, it's a choice that happens regularly. So once that happens, people gave up on trying to make the data, the memory, the same speed as the processor. They first panicked. They said, no processor can run. Then they came up with these caches, which is a great idea. We will talk about that at length. We will get bored of caches. And at the same time, you realize that since the memory is not as fast as the processor, whenever I connect the data memory to a processor, I need to make sure that I want something and the memory says, hey, the data is here. So there is a bit of handshaking agreement between them. I'm not throwing them in because I'm assuming implicitly that whenever I present an address, the data is here. In real life, in bigger systems, this never is the case. You can control this guy because you can build it internally, whereas the external data, external memory transfers always have a handshake. You say, I want to write to here. And then you hear back from him and says, dude, I did this. Or you want to read something, you say, this is the address. He says, this is, I have your data, and something writes and says data rate or something like that. There's always some handshaking going on. It was necessary because since, let's say, 1980s, the memory speeds cannot keep up with the processor speeds. And once you have that, it doesn't matter if it responds in 2 cycles, 10 cycles, 1,000 cycles, 1 million cycles. You do that, and for that, again, there comes the caches, which can mask his problem. And then, if you can manipulate the cache as well, you can almost pretend that you have a data memory which is the same speed as the processor, or very close. You also have to realize that you are not always reading and writing. So you can afford to wait a little bit to come to that as well. So there are cases where you can hide, we call this the latency. Whenever I write something and I expect this to be done, the start and stop of this operation is then the latency that we talk about. And you can hide the latency under certain circumstances. You cannot hide the latency if you, for example, write something and then immediately read it back. Yeah. And then you have issues, and we will also talk about it. So that's next week. Well, we can't do it in one step, right? We cannot do it in one step. We will have to. Well, it says that's fine. And now you say that what if this one is 100,000? Because guess what? 100,000 you cannot express this. But you also have T1 So you can manipulate T1 to be 100,000 more. So you can have a number of instructions to increase T1 and then manipulate the data. It takes longer. You take a bit more operation, but how many times do you actually need to access the data so far away? How often does it happen? So this is the choice of the guy who makes the instruction. He says that 16 bits would be enough. Maybe you are a different architect and you say, no, I need 20 bits because I see that in all my applications, I have a lot of data structures and making additional instructions for this is very disturbing. So you say, let me not do that. I just quickly need to clear this thing because it's confusing. I'll be right back. Okay. Yeah, I mean, all time is always the problem. However, when you look at the type of things you are doing, we are more likely concerned with setup time because the paths are very long. All time is only an issue if there can be short paths. Maybe I can come up with a good example and ridiculously short path. The single cycle thing, it would be very hard to find. I mean, it would be difficult to find something that would violate the whole condition. The particular thing that I have. That has nothing to do with hope. Absolutely not. Absolutely not. You're mixing two things. I understand where you're coming from. That has nothing to do with each other. Absolutely not. Because reading and writing are done in different cycles. They are separated by a cycle. So I read at the very beginning of the cycle. So then the clock cycle. So I'll just go into so I have the instruction. On the instruction, I have the read1 and read2 the algorithms. So I go to the next file. I go to the next file. I pick those things up. I go to the right? The ALU complex meaning the third register for us. And then I write back to this register. So I read the register. And now I'm going back to the register. The first part is done. So this is the right update. And this goes to the and this guy writes this, I write it back. So this is where I write it back. I have already. So there is no race condition whatsoever. This is not an easy operation. Because how do you read one of 32 registers? It's a 32 total multiplier. It's a lot of work trying to figure one of them out. I mean, we can talk about it later. But it's, I understand where you're coming from. I mean, it's all questions, but they are very different.
The ultimate technique run 6 seconds.
Yeah.
Okay. 32, no. 44 minutes to set everything straight. Let's go. Now, once again, this is the order at which the book Harris and Harris is describing these things. It's actually a very good way of explaining it. I just started in a different way. So let's start it again. What we understand is there are different elements that make up the processor. And some of them can hold state. So the state holding elements are the program counter, which is a 32-bit register. So this is the one that points to the next part. We have a part of the memory, which is an instruction memory. It's actually a bit of tricky thing. So if something stays in your mind and saying, why do I have data memory and instruction memory separate? It just makes this part explanation much simpler. In most practical cases, the instructions and the data will be in the same memory space, but they are very different at very different places of the memory. So seeing them as two completely independent memories makes my life explaining here much more easier. And this is why it's used like that. It wouldn't be so difficult to show that they could be the one and the same memory. So it takes a 32-bit address, and corresponding to that address, it will spit out the content that is residing in that address. Then we have register file. This is the thing that is inside the processor, and MIPS processors work on these 32-bit values, and it has two addresses for reading and one address for writing. The reason is a lot of operations like A plus B takes two input operands and generates one output operand. So you read two things and generate a result that you want to write back. This is why you want to have a specialized register file that manages two reads and one writes in the same cycle. It's a luxury, to be sure, but it is doable. And we already saw that, if you were to write down the code of it, it's not that difficult. Then we have a data memory. Now, the data memory, the expectation for that is to hold hundreds and thousands and millions of data words. So this is the thing that carries the bulk of your operation. So because it is so big, we cannot have it as fancy as this, where you can read and write multiple times. It has a single port. You can either read from it or you can write to it. If you write to it, it's the same address as the one you're reading from it. The difference is you have this write enable signal, which says that, look, this address you should write to. And if write enable is 0, this address tells you what data to retrieve from the memory. A question came in between in the class, in the break, that, how come these memories were slow and things, and now everything works so fast? This is also a simplification we are making just to explain things simpler. In real life and later in our lectures, you will see that our main issue is that this memory cannot keep up the speed of the rest of the system. So we will do a lot of funny things to mask the slowness of this memory piece. Just to beginning, now for the first few lectures, we will assume that magically this memory can keep up at the same rate as the processor can. Since 1980s, this is no longer really the case when we are making real processors. However, didactically, it makes a very nice story. So, we like nice stories. Is that okay? Great. So now let's go through one instruction. We have all our 4 parts. You see, we have the program counter. This program counter is now pointed to the instruction memory, and we got the instruction. The instruction that we have read out happens to be this one, load word, the content of this register, which is 0, add a constant value to it, in this case 1, and whatever is written in this memory address, please copy it to the content of the register S3. Now, this instruction, once we read it out from the memory, it's a 32-bit value, and looking at it, we see that it has different parts, and we realize this operation tells us that it is load word. We know that RT holds the destination thing, and the base address is here, and the constant is then encoded in these 16 bits. So this is what actually the instruction decoder is able to do. Now, the first part of the operation is trying to figure out what is the base address. We already said that the base address is here, so the bits 25 to 21, so if you count the bits, you will realize that these bits select the RS, and I'm able from the register file to read this thing out. Now, the lower 16 bits, this part of the instruction contains the constant, but the constant is only 15 bits. So I want to extend this 15 bits to 16 bits, to 32 bits. So this is the sign extend operation. We saw this at the very beginning when we were talking about number formats, and we said that we can use 2's complement, and if we are extending a 2's complement number, what we do is instead of adding zeros to the left of the number, we are actually adding the most significant bit, which would be 1 if it's negative, 0 if it was positive, to be able to extend it. So this number now is a 32-bit number that we can add to the base address that we have retrieved. And for this, we also have an ALU. The first part of the operation, this one came from the register file. The second part came from this thing. We added both of these things together. The ALU can do different operations, and we chose the operation that allows us to add these two numbers. And the result, the ALU result, becomes the address that will point to the data memory. Now, in data memory, once I present this 32 bits, I will get a 32-bit value. I'm taking this value because all the while I'm doing this so that I can write it back to this register. The register's address was written here in these bits. So the bits 20 to 16 point to the register file and say, look, the data that is coming here, all the way from here, should be written to this register. In this case, should be written to S3. And I should make sure that I'm writing, I owe a write to this register file, so that when the clock comes, this value will be copied into the register file. Okay? The next thing that we have to do is we will have to point to the next instruction in the memory. I had my program counter, and I'm incrementing it by 4, and I'm writing, and that will be the next instruction. So when the next clock tick comes, the next instruction, meaning the PC plus 4, will become my new instruction. I'll read something else. I'll decode what it wants. If I'm reading from the memory, I'll maybe do a second load word instruction. So I'll go back a few steps. And you see, these are the same steps that we are discussing here. We fetch an instruction. If you follow from the board there, we read the source operands. We decode what it is, then we read the source operands, we combine them together, we perform the operation, we get the data, we write it to where it needs to go, and then we repeat this cycle. To repeat the cycle, we need to point to a new address, and at the end of the cycle, I have my new address. Questions so far? It's getting better than 50%? That part is looking really, I'm trying, okay? Don't worry. There's still 35 minutes. So the store word is actually, oh, sorry, question.
The
That's a very good question. Let's just assume it happens by magic. Okay? It's a very justified, very valid question. You're not old enough to learn it yet, no. Let's not go into the details of that. Let's just assume that towards the end of the lecture, those things will become clearer, because the processor at the moment is also not communicating to the outside world. We are not getting any input from the keyboard. Somebody was asking, we are also not writing things to the hard disk, communicating over wireless and things like that. All those will be possible. Is an extension of what we are doing. And when the computer boots, actually, what happens first is that operating system or the first firmware is loaded into the system. That boots the system. So those parts can be done. The mechanics into which we are not going right now. I didn't sound convincing. You'll learn about it later. No, shut up. Okay. Single cycle data, but we are continuing. So what's the difference in a store world? And you realize that most of it will remain the same. I again have a register. I have two registers basically. This is the base address. So I'm going to pick the base address. I'm going to sign extend this thing. I'm going to generate the address to the memory. But this time there's a difference. The difference is this time I'm not writing to the register file. So I don't care what the input to the register file is or who goes there. I mean, I'm not writing anything to A3. But this register now, the T7, has to generate the value that gets written to the data memory. I have the address. I have the data that will get written. All I have to do is make sure that the memory also knows that I'm writing. So I have a control signal that says memwrite. I apply 1 during this cycle, and voila, I generated the address the same way to the data memory. So there's nothing different. But the difference is now I actually read, I use the address A2, and this one becomes gives me the data that will be written to the data memory. That was actually a quick jump. Load word, store word. Okay, it was too much repetition. So at the moment, I'm having a bit of trouble because I repeated it like 3-4 times. I'm not sure if I'm boring you or it's good. So thumbs up, thumbs down is, okay, yeah, okay. Ankara is not happy. Okay, so when I was explaining it, I started with R types. In the way that it's explained in the book, we go from load word to store word and then to R type. And in R types, I now have 3 registers, and I'm not doing anything in the data memory. What happens is, once I pick the instruction, I have the 2 operands that go into the ALU. And the difference now becomes that since I have 3 registers, I have an issue selecting where the destination is. Because in the previous one, the destination was here. In the R type, the destination is here. So I have 2 different options where I'm going to be writing the result back to. It's either these bits, 20 to 16, or it's these bits, 15 to 11, and I have 1 multiplexer to choose. Why did I do this? Well, the architects who decided on this encoding made this compromise. Honestly, I have no clue. It seems to me that it would have been easier to always use the second register as a destination. But what do I know? There is probably a very good reason. Trust your elders. The good news is when you are, there's no more discussion when you have made these different abstraction levels. The job of the architect is to determine the instruction set and how the things work and define it. What we are doing right now is implementing it. We may not like the architecture. I mean, you know, we are engineers, we are very opinionated people. We usually bitch and moan about various things. So, you know, why should this be any different? But there's a clear distinction of things. If you want to do the, if you want to be the torturer of microarchitects, become a computer architect and decide on the architecture, then you can play with microarchitecture guys. Anyway, so I have a difference here. I also have a difference for the source of the ALU, because previously I was always taking this immediate as one of my operands, but now I have another option for an R-type instructions. The second operand to the ALU comes directly from the register file, and I know where to pick this from these bits 20 to 16. So they provide me this. Now the ALU result used to go as an address to the data memory. It can still go there. I don't care, because I'm going to ignore the output of the memory. What I will do is I will take the result of the ALU, bypass whatever the memory I was reading from memory using another multiplexer. I told you I like the multiplexers, right? They are so cute. And then I'm going to bring it back and write back to the register file. Okay. I see. I'll speed up. The other instruction that we were really interested was to make a jump. And it is, again, an I-type instruction. So we have an offset to my current location in the program. So this is where my program would normally go. I will jump to an address that is offset by the immediate adjusted forward size. And then if the jump is successful, if I'm taking the branch, the program counter will not be program counter +4, but will be this new put together address. PC +4 plus that immediate. How do I decide on this? Well, I'm going to compare these two, the content of these two registers. If they happen to be equal, and I'm branching, I will say, hey, let's do this thing. How do I force this thing? And you say, hey, the ALU already does a lot of the job. I will subtract the content of register 1 from the content of the register 2, and just make sure that they are all equal to zeros. That was a simple operation, could be easily added to the ALU, so that it can generate a special, hey, the result of the previous operation was a 0. If the result of a previous operation was 0, and I am branching, this means that we should maybe select the other one, the branch target address, as my next location where I'm getting my instruction from. So this completes all this thing. The control unit now is the one that receives the instruction. This is the one that I drew with a blue cloud at the bottom, because it was easier for me to write at the bottom. And it generates all kinds of these blue control signals that determine whether or not I write, which operation I do, what is the condition of these multiplexers here and there, and that one, and decides for every cycle what is happening. So we also have maybe the control unit. This is a little bit detailed, but we have the opcode, which tells us what to do. There is a special opcode where you realize you have an R-type function, and then you look at even more bits. Those are the lower 6 bits, so that you can tell what the ALU is supposed to do. And the ALU could add, subtract, do a number of things. So this was our ALU. Repeating it again, so I can pass this very quickly. And then everything can come together. You can decide at which point what signals are being generated. Once you have these tables, it is easy to write your code, or even if you are up to it, you can also do the optimization yourself. You know, we saw all these Carnot maps and things, how we can minimize things. And for the main decoder, you realize that this is the table we already walked through. Given the instruction, once we look at the operation code, we know what the individual control signals should be. So at every step of the way, what we say decoding is looking at the instruction and deciding on the rest of the way, controlling how the data will be flowing through. Is the ALU is always getting some input here. Is this input coming from the register file, or is it coming from this sign extension unit, which is tied directly to the instruction? I'm always having something that comes back here, but is this data coming from the memory, or is it coming directly from the ALU? And if the data comes here, am I actually writing it back to the address shown here? Where does that address come from? Does it come from these bits or these bits? Those are the decisions that this control unit is making. It is not trivial, let's say. You make the decision. The microarchitecture says how we are going to do it. Now, from the beginning of the lecture, we are saying that we will do this in a single cycle. So this is a single cycle architecture. And in a single cycle architecture, we are insisting that everything happens in one clock cycle. It's not necessarily the best way. It's not necessarily the worst way. It's just one way of doing things. Now, we could extend the operations. You know, we can have OR, and in OR, you know, program counter reads instruction, realizes OR, picks two operands, goes through the ALU, ORs them together, jumps over the memory, result comes back here. The address to write back is being calculated here. This guy says, pick this one tells it, and then we are done. Now, you can also start adding new instructions. Notice that and or all of them were R-type instructions, but you can also add new functionality like add immediate. Now, previously, whenever I was adding an instruction, we needed to modify the data path. We realized, oh, I need this more. Oh, I need also this. Here a multiplexer, there a multiplexer. It's not always like that. And add immediate is a good example. Because you realize now after I've added a couple of instructions, I have something quite nice. And by manipulating the control signals only, I can have different instructions, because what you realize is I will need the sign extended thing. I have my register, I can add them together. I was doing this, and I have the ALU result. But now, previously, whenever I had the sign extended value, I was using it as an address. I don't have to. I can just bypass the memory and write it back. So in this case, implementing this instruction is actually a different entry in our control table. So when I come here, this is a new instruction. Now you realize that, hey, it's an R-type instruction. It's very similar to this thing. I am using these things, but I am not writing to the memory. And voila, just by manipulating, let's say, the control path, I can have a different functionality. Was that too fast? Makes sense, right? I mean, it's always the same story. Okay. So this was the last thing we were talking about, extended functionality. We look at the instruction. We take 26 bits from here. We say, hey, those 2 bits, we know how to do it. They are all zeros. And then I take the PC plus 4 and copy its 4 bits. So those are the additional bits I was talking about. Those are the 2 bits that I saved. The 26 bits I directly got out of the instruction. So I have my 32 bits. And if I am jumping, I know my address, so I can just immediately manipulate it. How does it look like? Well, it looks exactly the same. I now have a new control signal that says, guys, we are jumping. So this concludes me trying to explain these instructions. So this part of the slides, if you're watching this, is exactly identical to the way it is being described in the book. So if you want to refresh it, study on your own time, you can use this part of the slides and, you know, read together with the book. It should answer most of the questions. To understand what's going on, I believe it was sort of necessary to look at it. Now we come to the most interesting part. As I see people leaving, most interesting part. You have no idea how interesting this will be. People have places to be. Don't be mean to them. It's not nice. this is what we ultimately care about. I mean, all this blah, blah about instruction sets and doing this and doing that, it comes down to how well does my program execute and how fast is my program. And it is really how long do I wait for this result to be here. So every program consists of a series of instructions, and each instruction needs to be executed. I need to complete it. And the question is, how fast are my instructions? So I realize them on hardware, and it doesn't always have to be one cycle. It can take one cycle, it can take multiple cycles. You will see that it can also take fractions of a cycle. Wow. And we define cycles per instruction. How many clock cycles do I need to finish one instruction? And once I know this, the question is, how much time do I need for one clock cycle? Because we said that we want to, we had this entire data path, PC updates, we read something, we multiplex, we add, we multiplex some more, we multiplex until we die, and then we need to write it back. All of this takes some time. And this time needs to be enough. I need to give it enough time. My clock cycle needs to be long enough to complete it. And what we define the critical path is all of these operations that I was making, some of them are more difficult than the others. When you make a load word, you first calculate, you take the register, you add things, you read it, then you read from the memory, then you write back. Whereas some of those, like the jump, was directly, you saw the jump, you already have 26 bits, you add a couple of more bits, and then you have your next thing. You're not writing to memory, you're not writing this, you're not using the ALU. You're basically lazy, everything is here. 26 bits are here, 2 bits are for free, and the 4 bits you are stealing from the PC plus 4. How difficult is that job? Okay, so that one completes much faster than loading a word from the memory. However, whatever is the most difficult operation, you will have to reserve time for that. You cannot say, jump, I can finish in a nanosecond, but load word takes 10 nanoseconds. Well, if it's 10 nanoseconds, that's the time I can do it. 10 nanoseconds means 100 megahertz, 1 over. So 1 over the clock period gives the clock frequency. And that says how many cycles can be done each second. If I finish one clock in 10 nanoseconds, I can run at 100 megahertz. That means that I can do 100 million instructions per second. Right? That should be able to, bring up a browser or something. Now, as a general formula, and believe me, you will study these things forever. It doesn't get more complicated than that. It's this simple. Our program consists of executing n instructions. Our processor needs CPI cycles for each instruction. This one could be an average, it could be an aggregate because we might have some instructions that take longer, some that take shorter. In MIPS, all instructions take the same. People wanted to cheat here and make life easier. The maximum clock speed of the processor is f, and the clock period is therefore 1 over f. That's the time I have for one thing. And our program will execute in n times. So these are the number of instructions I have to execute. This is how many clocks per instruction I need. And this is how many instructions I can do per second, right? And if you look at it, it will take so many seconds. So this is the period, CPI times n. This is it. Nothing very, very fancy. Now, when you look at this, this also tells you what you can do to make the program run faster. And this is the essence of it. There's nothing magic about it. Number one, reduce the number of instructions. If you can make the same functionality using less instructions, you'll be faster. One way for making it is, make instructions that do more. Instead of, having an instruction that can only add 2 operands, why don't I have an instruction that does an FFT? Would be great. The second one is, that we have a high-level language describing it. We don't write code. Some of us do, but we don't usually code writing ones and zeros. If this was in the curriculum, I don't think half of you would be sitting here. You want to write high-level code. What's your favorite? What's the favorite language here? Of course. 2 Rust guys and the rest? Sorry? Python. Who loves Python? Okay. Oh my God. Let's fight about it. Don't fight against the Rust guys. They have those crabs they can shoot at you. Okay. You can use better compilers that takes your high-level code and turns it into a more efficient set of instructions. And there is a lot of room of improvement there because we hide a lot of performance things in there. And when people write code, they are very far away from all the tips and tricks that we are doing. We rely on the compilers, which is things that you guys do, on being able to squeeze the most out of it. You can see how well this thing is going, for example, on PlayStation. The PlayStation hardware didn't change, like PlayStation 4 hardware didn't change the last 7-10 years. The games got better. How come? Well, people learned how to write things better, better libraries, better compilers that enable people to write things that seem to make more. So once the hardware stops improving, there will still be a lot of room to make things better. So this is the first trick you can make. Manipulate the end. Use less cycles to perform the instruction. Well, if the instruction is relatively complex, you have to do a lot, maybe 1 clock cycle is not enough. So you have 3 clock cycles per instruction. If you have simpler instructions, maybe you can drop the CPI. And this was the motivating idea between the risk-like structures. They said, if you make simpler instructions, we can afford to make single cycle or fewer cycle words. Then the second thing is, why do I do 1 instruction per cycle? Why can I not pick 2 things and do them in parallel? Why don't I pick 5 things and do them in parallel? Are you taking parallel programming courses? Right, so that's the idea. Let's also do it in hardware. Why only in software? So I can use multiple units, ALUs, cores in parallel. As long as I can get the benefits of parallelization, this is great. Exactly. Life is a trade-off, right? So this one says more, this one says yes. So the idea is, can I reduce the CPI more than I increase the N? If there was a simple answer, we would be having 1 architecture. So since there is not one obvious answer to that, this is the thing. The second part is, now this has more to do with the architecture, this has to do with the compilers, and this one has to do with the technology. Increase the clock frequency. Why are you running it at 100 megahertz? Run it at 10 gigahertz, 100 gigahertz. What's the next one? Petahertz, whatever. So some of it has to do with, those annoying things I was talking about, transistors, how they are made, parasitics, switching, capacitance, blah, blah. And maybe we can find newer technologies to manufacture that allows us to switch faster, do the same type of operation with less effort, in faster way. We realize that there are some components, like I'm adding numbers all the time. I'm making 32-bit additions. And if you remember, we were talking about like this curse of the carry. Guess what? There's so many adders there, and all of the adders are cursed. Like haunted house, horrible. We can redesign time-critical components, or we can do something that we call pipelining, which seems like a magical thing. That's our topic for next week. We will realize that, hey, we can actually increase the clock frequency without changing the technology and maybe not touching so much the critical components, and everything will be okay. Never believe someone that says that. We will pay the price. We might be willing to pay the price. That's the type of thing. Okay, so very shortly, let's just think about what is the performance bottleneck in our processor. So the period is limited by the critical path. Now, there could be as many as 100 different instructions here. And depending on the instruction, depending on the constants and things like that, we might realize there's not only a single path here. But when you make an analysis, you will realize that the load word is one of the most annoying instructions to realize in this particular architecture. So somebody, I had a class of 50 people. I asked every one of them to figure out which instruction, how long does it take. And the person who was doing load word came up and had the highest number. So this is how we know we analyzed it. And if you think what is happening is, first I have this program counter. I read from the memory. That takes some time. Then I read out from this register. Takes some time. Then I make an addition. And that addition gives me a result that becomes the address. Then I make yet another read. And then I go through this multiplexer. And then I arrive at the register file. At this point, the clock can arrive because I have finally retrieved my data. Now, the annoying things we talked about timing will come in here because, well, this is a register. The clock comes. There will be a propagation delay. This is a combination logic, propagation delay, combination logic, propagation delay, combination logic, propagation delay. I'm tired. Propagation delay, propagation delay. And I'm about to write in here a setup time to be able to do this. Now, this just writes these things. So the propagation delay of the PC, the time of the memory, I have actually two paths that go parallel. So I either make a register file read, or I do the sign extension and go through the multiplexer here. So I have two paths, whatever is larger. So either this time to sign extend. Notice that it's not a very difficult operation. Just appending. Multiplexer is usually cute. Reading this is horrible. And then the ALU, then another memory, then another MUX. Then I go to the register file setup. Clear so far? So this is the setup constraint. Now, if I know the numbers for these things, we can directly calculate it. And they are right. The most annoying things, the most difficult operations, so this is if you have some experience and design them, if this is your day-to-day job, you'll realize that these memory reads, register file read writes, ALU, those are the things that take time. The multiplexers, extensions, shifts, and things are relatively benign things. Anytime you are adding, reading, writing to memory, oh my God. Don't do that. So the book chooses some numbers. They are not bad. They're not that great. But given for every element that you have, if you have the numbers, you can just put the numbers together and we make a calculation. I mean, how hard can this be? If you're in an exam, if you're stressed for time, obviously this is where you make all the mistakes. TPC, QPC. So this is the register to clock. Propagation delay 30. Okay, 30 plus. I'm picking 2 times memory because I make 2 memories. Once for the instruction, once for reading the data. Memory read was 250, 2 times 250. Okay. I read the register file. For some reason, it's faster. Makes sense because the register file is smaller. The other guy is bigger. Why not? And then I go through a MUX. I said the MUX, those things are, Kleingemüse, 25, whatever. ALU, here we do real work, 200. And then another register file setup, throw in another 20 picoseconds just for good measure. Okay, we sum all of them up, 925 picoseconds, almost a nanosecond, almost a gigahertz. Doesn't look so bad. Questions so far? Now, I would ask the following question. How do I know this is the longest path? As I said, there are actually tools that can calculate from every source to from every flip-flop output to every flip-flop or state holding element input. They can automatically calculate all the paths, do it automatically for you. As a designer, you also know what your paths are. There's also one path that, for example, starts from here, goes through this program counter, comes back, goes through the multiplexer and writes back. However, I told you, like additions is long, multiplexers is short, but this one has memory, addition, memory, mux. No comparison to a single addition and memory. But knowing your path is one of the issues. Now, we want to calculate how much this thing can take for a program with 100 billion instructions executing in a single cycle MIPS processor. Okay, let's put the numbers. Execution time is number of instructions times CPI times the time constant. So we have 100 billion instructions. CPI is 1. I use 925 picoseconds or 0.925 nanoseconds. And if the calculation is correct, wait 2 minutes and 100 billion instructions will fly away. 100 billion instructions. Do you know how much it takes to boot Linux? 7 instructions? Load word, load word, load word I, load word N, load word U, load word X, yeah? Any guesses? Depends obviously on the architecture and things like that. I mean, we were using a RISC-V core, it's about 2 billion cycles, 1 to 2 billion cycles. It's simple, you know, we are not waiting for the devices and things like that. Okay, so now we have an argument. What did we learn? This part, trust me, if nothing from this lecture, that part where you discuss about how to make computation faster, that thing, we will iterate it in many, many different forms. The basics will not change. Either we have to do more per clock cycle, increase the clock speed, or decrease the number of instructions, or a combination of them that is more advantageous than what we have at the moment. This will be our challenge whenever we want to do things better, faster, nicer. This is what we will be doing. We learned the single cycle MIPS architecture. To be honest, this is not the way we will do processors. It explains what we do very well. All the steps, all the effort that we are making is going to be used one-to-one. Now in the book, they go and explain a multi-cycle architecture. Just very briefly, we will not be touching that, but what you realize is you are accessing memory, you are adding, subtracting, you are accessing memory. The idea in a multi-cycle architecture is not to have multiple units do the same thing and reuse the things. And so in one cycle, you will read from here, in one cycle, you will do this, in one cycle, you will do this. It gives you the flexibility to reuse the components. It's kind of recycling of the things. You do that because you are strapped for place. You don't have many resources, so you want to squeeze things as much as possible. We are not going to touch that part. If you're interested, you're not responsible for it in the exam, if that's what you're concerned with. If you're interested, you can read through. It will look very similar. The only trick is we are trying to reuse the components. The components cannot magically disappear. They will still be there. They'll just be used in a different way. And what we will talk next week is we will not be happy with the performance, and we will try to increase the performance. And what we will try to do is pump up the frequency without changing too much what we are doing. And we will see there is a great way of doing this, which will be called the pipelined architecture. It is great. I'm not going to lie about it. It's really gorgeous. But it has some stupid price you have to pay. And on Friday, we will be talking about the price we have to pay. On Thursday, it will be the great lecture where more people are here. We are going to explain how great it is. So thanks a lot. Enjoy the weekend and talk to you next week.
Timing was not bad though. Almost perfect.
So my question is, when you use branching operation, branching instruction, we first add 4 to the address, then add the address that you're planning to go, right? Why do we add this 4?
Why not?
But like the address we give is already the one that we are trying to branch to, right?
No. Yeah. The address we are going to is Well, if we weren't branching, the next address would have been EC plus 4.
Yes.
So the branch says